Okay, guys, so I saved this example for a video all by itself. The process that we're going to go through is the same as what we've been going through, but you'll see why this one is a little bit more complicated. So they give us a reaction, and they're telling us, here's my reaction. They're telling us what the equilibrium constant is equal to. And they're asking us for concentrations. Okay, so we need to set up our little ice table. So I'm going to write out the reactants, and here's my product. Okay, I have initial, change, and equilibrium. Okay, so a mixture of 0.2 moles of N2 in a 1 liter container. So again, they didn't give us molarity, but if I take 0.2 and divide it by 1, I get the molarity of N2, which is 0.2. And they're telling us I have 0.15 moles of oxygen. And if I divide that by 1 liter, I get the concentration, the initial concentration of oxygen. And as always, guys, I didn't start the reaction yet, so I did not make any products yet. Okay, for my change column, I want to always make my reactants go down. Since they don't have coefficients, they're only going to go down by x, not like a number associated with x. And my products are always going to go up. Since my product has a coefficient of 2, they're going to go up by 2x. Okay, and then to get my equilibrium row, I'm going to take these two rows and combine them. And 0 plus 2x is just 2x. Okay, so next thing I'm going to do is I'm going to write out my equilibrium expression, my KEQ. I'm going to take my products squared because they have a coefficient of 2, divided by the product of my reactants. They don't have coefficients, so I don't have to worry about squaring or anything like that. Okay, so now I'm going to just draw an arrow here. I'm going to plug in what I know. They gave me the equilibrium constant to be 4.1 times 10 to the negative 4. So 4.10 times 10 to the negative 4. And that's going to equal, I'm going to throw in the numbers that I just figured out. My product has a concentration of 2x, and my reactants are, and that has to be squared, my reactants are 0.2 minus x times 0.15 minus x. So it's at this point, guys, that I can see that this is going to be difficult to solve. I don't have a perfect square in my denominator where it's the same thing multiplied by each other, where I can just simply say, hey, let me square root both sides, get rid of these squareds, and keep on going. So at this point, I have to use FOIL to figure out the denominator. So I'm going to just rewrite this times 10 to the negative 4. If you guys don't mind, I have to, if you see how slow I'm writing, it's because my computer's going to die. Let me just plug this in. And that should speed us back up. Okay, so I'm going to still have, let's see, if I take 2x squared and I actually square it, I'm going to get 4x squared on the top. And if I use FOIL on the bottom, I'm going to get x squared minus 0.35x plus 0.03. So this is just like ugly. And if you guys don't remember how to do FOIL, it would be great if you could actually pause the video and do that, first, outer, inner, last, combine like terms. If you don't remember how to do FOIL, that's something that we'll need to talk about in class when we're together. All right. So now I have this. So if I throw this over 1 and I cross multiply, that's going to be my next step. I'm going to get this horrible, horrible looking thing. So let's see. 4x squared equals. So now I need to multiply this 4.1 times 10 to the negative 4 by everything in this denominator. It's going to be like distributing to everything. So I'm going to actually write this out as decimals instead of continuing to write it in scientific notation. To me, it just looks nicer. If you'd rather write it in scientific notation, that's fine. But it's going to be point, if I'm multiplying 1, 2, 3, 4, 1 x squared, right, minus 0.0001435. That's what I get when I do 4.1 times 10 to the negative 4 times 0.35 x. And then plus, now I need to multiply 4.1 times 10 to the negative 4 by 0.03, and I get 0.0000123. Ugh. Now, what I can do is I can get these x squareds to be on the same side and set this whole equation equal to 0. If I minus 4x squared from this side, I get 0. And if I minus 4x squared from this side, I get negative 3.99x squared. And then I'm just going to copy everything else. 0.00143.5x plus 0.0000123. Okay, so guys, at this point, I can figure out what x is by using the quadratic equation. I don't know. I know that you guys must have learned a way to memorize this equation in math, and it's probably different than what I learned back in high school a billion years ago, but I'll say how I know it. So x equals, my math teacher said, never be for or against radicals, be squared against 4 alien creatures who divide to attack. I have no idea what that means, but I memorized it in high school and I still know it, so I guess it worked. So when we have the quadratic equation, we look at the setup that we have here, and the number that goes with the x squared is what you're going to plug in for A. The number with x is going to be with B, and the number that has no x with it is going to be your C. And you're going to take these numbers and you're going to plug them into this quadratic equation. To save time, guys, I'm going to set it up, but then I'm just going to solve for it. So x equals, I'm going to plug 0.0001435 in for B, plus or minus. I'm plugging B in again, but I'm squaring it this time. 0.0001435 minus 4 times A, negative 3.99 times C, 0.0000123, divided by 2 times negative 3.99, which is what I had for my A value. Okay, so this is like a nightmare. So when you plug this in, you're gonna get x equals 0.0017 or 0.0018. Whether you added or subtracted here, these numbers are so small, guys, that whether you add or subtract, you're getting close enough to the right answer. So if I know what x equals, I can go back and plug that in here. So if I plug 0.0018 in for all these x's, then I can go ahead and calculate what the concentrations are going to be equal to. So 0.2 minus 0.0018 is 0.198. So that would be the concentration of N2. 0.15 minus 0.0018 is 0.1483. That would be the concentration of O2 once we reach equilibrium. And 2 times 0.0018 is 0.0034. So whether you use, guys, I might have plugged in the 0.0017 when I initially did my calculations. I think I plugged in the 7. Yeah, because that would have made me come up with a 4. Yeah. So whether you plug in the 0.0017 or the 0.0018, it really shouldn't matter because it should be so close. So I found all the concentrations of everything that I was supposed to, and that's what they asked me to do. They asked me to find the concentration of NO, which means that this is really just the only answer I need to square. That's what they're asking me. But it was a super duper, really annoying process. So what I want to show you is I want to show you a way that you can cheat so that you can still get the right answer without using the quadratic equation. And you're going to cheat by using the 5% rule. If the equilibrium constant is less than 1 times 10 to the negative 4, that means it's a very, very, very small value, which means that not a lot of products are being made. You're doing a very small number divided by a big number. So if you don't have a lot of products being made, you can actually ignore the minus x in the denominator. And I'm going to show you what I mean. I'm going to change my color so that this makes sense. So what they're saying is that so little reactants turn into products that I can forget this minus x. I could literally cross it out like it didn't exist because we're subtracting such a small number from that number that the change is like so small, it's negligible, it's insignificant. So if I get rid of that minus x value in my reactants, I can still go through this process and come out with the same answer that's close enough to being the same. So let me show you how that works. I'm going to do my equilibrium constant. See how it's super small? 4.1 times 10 to the negative 4. So that's what should clue you into. You might need to use the quadratic equation, and I might be able to do this little cheat sheet. So on the top, I'm still going to have 2x squared because my products are not allowed to change. But on the bottom, instead of having 0.2 minus x times 0.15 minus x, I can forget the minus x. And let's see how this works out. So I'm going to rewrite this. 4x squared. Now I can just multiply those two numbers on the bottom. So 0.2, let's see, times 0.15, 0.03. Okay. If I throw this over 1 and I cross multiply, 4x squared equals 0.03 times 4.1 times 10 to the negative 4. 0.000123. If I divide both sides by 4, I get, still annoying, but not as bad. And you guys don't have to write all these steps out. I'm doing it so that you can see it. 3, 1. If I take the square root of both of these, x equals, let's see, answer 0.0018. Look, I got the same answer twice. Okay. So was I allowed to use this 5% rule, this cheat sheet rule? Yes. Now, it's stupid to use a shortcut if you have to do the question twice. So I'm not telling you to use the quadratic equation and then use the shortcut and make sure you get the same answer twice, because that's like more work for you. What you want to do is just automatically, when you see that this is a very small number, automatically use the shortcut and then find out if this is less than 5% of the initial concentration that was given to you. So how do we find percent? I'm going to take what I got for X, 0.0018, right? And I'm going to go up to my original reaction. Okay. Okay. So if, oh, this is kind of a funny one. Okay, so I'm going to go up to my original reaction, and I'm going to take 0.2. So 0.2 was my initial concentration, right? So if I take 0.2 and put that on the bottom, I want to calculate the percent. So 0.0018 divided by 0.2 times 100. 0.9%. So only 0.9% of the reactants turned into products. Is that smaller than 5%? Yes. So that means that I was allowed to do it this way. So that's what I would do, guys. I would forget all this, do it this way, and then at the end say, is the X that value that I got less than 5% of my original amount? And if it is, that means you were allowed to use the shortcut and you can just move on. So that's nice and easy. Okay, last thing we're going to talk about in this video. Oh, look how much room I gave myself. I guess we didn't need all that room. Manipulating equations effect on KEQ. So guys, when you do something to an equation, when you change the equation, you're going to change its KEQ, but there are easier ways to figure out how the KEQ is going to change without like starting over and doing an ice table all over again. So let's say that this is my original equation, and I'm just going to make a number. Let's say that for this reaction that I gave you, KEQ is equal to 10, right? Now, if I look here, I reversed the equation. I took the products and made them the reactants, and I took the reactants and made them the products. So reversing the reaction, you need to use the reciprocal for the KEQ. So if my KEQ was 10, now that I flipped the reaction, my KEQ is 1 over 10, or 0.1. Okay? Here, I doubled the coefficients. So if you double the coefficients, you're going to square the KEQ. So KEQ equals 10 squared, which is going to equal 100. So those are, again, these are just more shortcuts for when they change an equation in equilibrium and they want you to get KEQ. All right, so that's it for equilibrium, guys. In our next video, we're going to talk about things that actually stress out equilibrium and how reactions deal with that stress and get back to a place of equilibrium. All right, I will see you guys in class tomorrow. Have a good day.